Okay, welcome to The Explainer. Today, we're diving into the visually intimidating world of NMR spectroscopy. If you've ever stared at a spectrum and wondered how a chaotic forest of peaks could possibly reveal an exact three-dimensional molecular structure, well, you are in exactly the right place. We're going to take that messy, overlapping data and transform it into a solvable puzzle, specifically focusing on measuring coupling constants from first-order spectra and navigating the wild effects of strong coupling in second-order spectra. Let's get into it.
Here is our roadmap for untangling these complex signals. We'll start with a quick refresher on nuclear spin, define the coupling constant, decode some first-order spectra, and then look at what happens when strong coupling takes over. Finally, we'll check out how high-field spectrometers offer a pretty elegant hardware solution. Moving right into Section 1, Basics of Nuclear Spin, or as I like to think of it, the magnets inside us. To really make sense of the mess of peaks in a spectrum, we've got to zoom way in on the atomic nucleus itself. As you know, not all atomic nuclei possess spin, but hydrogen is our star player here. When we drop these spinning, charged hydrogen nuclei into a massive applied magnetic field, they basically have to make a choice. Just like literal bar magnets, they're either going to align with the applied field, which is a nice, stable, lower energy state, or they'll oppose it, sitting in a higher energy, unstable state. The magic of NMR happens when we zap these nuclei, making them absorb energy and flip between these spin orientations. But remember, they aren't just acting in isolation, they are constantly talking to their neighbors. Which brings us to Section 2, defining the coupling constant, the universal translator. So to actually translate these spectra, we rely on a critical metric called the coupling constant, represented by the letter J. Think of J as an invariant physical measurement of how strongly one atomic neighbor is whispering to another. When adjacent protons interact through their shared electron bonds, they split each other's signals. The physical distance between those split peaks, that is your coupling constant, and it's always measured in hertz. Take ethyl iodide, for example. The coupling constant between its interacting protons is exactly 7.5 hertz. It's a fundamental, unchangeable property of the molecule itself. And there is a really hard line here between our two main metrics, chemical shift and the coupling constant. Chemical shift, which dictates where a peak drops on the x-axis, totally changes depending on the magnetic field strength of your machine. If your lab buys a bigger, badder spectrometer, that chemical shift measured in hertz gets larger. But the coupling constant? No way. It's a physical truth. Whether you're running a 60 megahertz machine or a 100 megahertz machine, the J value for ethyl iodide stubbornly stays at exactly 7.5 hertz. The spacing between the lines of that multiplet simply does not expand. Let's move to Section 3, decoding first-order spectra, untangling the tree. Armed with that absolute, invariant J value, we can systematically extract the exact structural connectivity of a molecule right from a clean first-order spectrum. When you hit a complex multiplet, like a doublet of doublets, honestly, don't panic. A lot of folks take the easy way out and just slap a multiplet label on it, which is basically throwing away rich three-dimensional structural data. Instead, try this methodical subtraction approach. First, number all your lines. Your first coupling constant, J1, is just the distance between lines 1 and 2. J2 is the distance between lines 1 and 3. Now to find J3, you mathematically remove the multiplet component that corresponds to the sum of J1 and J2. This keeps you from mistaking a combined peak for a unique interaction. Once that's out of the way, J3 is just the distance from the first component to the next highest remaining one. You just iterate through this subtraction until you've bagged all your J values. It's like a perfectly logical puzzle. All right, Section 4, when strong coupling happens, crossing the threshold. But what happens when those neat mathematical rules completely break down and the spectrum becomes basically unreadable? Well, it all comes down to a single magic number, and that is the delta nu over J ratio. Delta nu is your chemical shift difference between two groups of protons, and J is the coupling constant linking them. If that ratio drops below roughly 6, we cross over from the beautifully predictable world of weak, first-order coupling, straight into the chaotic realm of strong, second-order coupling. The chemical shifts of the two interacting groups are just way too close together relative to how strongly they are actually coupled. Which takes us to Section 5, visualizing second-order spectra, the descent into chaos. Let's visualize exactly what happens to our data when that ratio shrinks and second-order effects completely take over. If you look at a simple two-proton system where the ratio is a healthy 15, you get a weakly coupled AX system. The peaks are clean, the intensities are equal, it's perfectly readable. But as those chemical shifts creep closer together and the ratio dips below 6, the peaks literally start to warp. The inner peaks shoot up in intensity, leaning in toward each other in what we call a roof effect, while the outer peaks just kind of shrink away into the baseline noise. By the time that ratio hits 1.5, we're looking at a messy A-B system where you can't even directly measure the J value anymore. And when the ratio hits 0, they merge into a single A2 line, completely hiding the J values. Throwing just one more proton into the mix creates an absolute cascading visual mess. With a 3-proton system starting as a readable AX2 system, it's fine at first, but as that ratio shrinks, intermediate peaks start shooting up out of nowhere. We go from a nice, predictable triplet and doublet straight into a chaotic AB2 system. You could theoretically see up to 9 lines here. And the crazy part is, the direct line spacings no longer correspond to the actual coupling constants. And this really shows the sheer futility of trying to extract simple J values by hand once strong coupling takes over. Take a 4-proton system. At a comfortable ratio of 10, it's an A2X2 system, basically just 2 neat triplets. But if that ratio drops to 1.5, it warps into a deceptively complicated web known as an A2B2 spectrum. You might see 14 distinct lines, and absolutely none of them represent a simple, extractable coupling constant. If you try to force first-order rules onto this mess, you are going to arrive at completely wrong structural conclusions. Which brings us to our final section, Section 6, the high-field spectrometer solution, buying clarity. Fortunately for us, analytical chemists have a very practical, albeit incredibly expensive, hardware solution to this quantum problem. Remember our golden rule about coupling constants? They never, ever change. But the chemical shift difference, measured in Hertz, absolutely does change based on the power of the magnet you're using. So by upgrading to a high-field spectrometer, say dumping that old 60 megahertz machine for a shiny 300 or 500 megahertz beast, we artificially increase the distance between the peaks in Hertz. Since the J value stays exactly the same, we're basically artificially inflating our ratio safely past the number 6. We are literally forcing a strongly coupled second-order system to behave like a nice, weakly coupled first-order system. When you look at the actual data for a molecule like 2-chloroethanol, the transformation is pretty stunning. On one hand, you have a chaotic, overlapping 60 megahertz mess, a classic second-order nightmare where the ratio is somewhere between 1 and 3. But look at the exact same molecule run at 300 or 500 megahertz. It is beautifully resolved. You can literally see how sheer magnetic power forces the data right back into clean first-order patterns. At 500 megahertz, our ratio hits 12, and that complex web seamlessly reverts into 2 clean, easily readable triplets. So we've seen how understanding the unchanging nature of the coupling constant lets us untangle complex first-order spectra, and how raw magnetic power can pull order right out of strong coupling chaos. It really leaves us with a fascinating thought to chew on. As our magnetic technology continues to scale upward into the 800 or even the 1,000 megahertz range and beyond, what entirely new chemical frontiers are we going to unlock? What previously invisible structural secrets of biology and medicine will we be able to effortlessly decode next? Thanks for exploring this topic with me today, and I'll catch you in the next explainer.